Thank you so much for listening in. As always, audio is provided via the internet, so please enable your speaker and mute your microphone. If you have any questions, there is a Q&A tab at the top of your screen. Please use this mechanism to type any questions you have at any time, and I will read them and answer them probably at the end of the webinar. Today we will discuss applying the principles of the safety life cycle using a sample problem of a batch chemical reactor. We're going to analyze a high-pressure hazard scenario from start to finish. The idea for this webinar actually came from a colleague of mine. He was asked to do a guest lecture at a process safety course at a local university, and he wanted to show the students how we would analyze one safety instrumented function, how we would implement it, and how we would maintain it. So we input all of the information into our Excellentia tools. And what I'm going to show you today is how we did that, and you'll see some screenshots to show you exactly what we did. My name is Kate Hildenbrandt. I am a sales engineer here at Exida. My role is to provide training and application support for our customers using Excellentia, SILSAT, and anything else. If you have any questions, you can come to me and I can answer them for you or find someone who can. So today I'm going to give you an overview of the safety life cycle. I'm going to introduce a sample problem and then go through each phase of the life cycle as it's listed here. We're going to do a deep dive into each task that you would do using our Excellentia tool and our SILSAT tool. So let's start with the overview. You might have seen this before on our slides. It's a pretty good overview of the life cycle. The safety life cycle provides a method to analyze, implement, and maintain a safety instrumented system from project scope definition to decommission. So as you can see here, the first phase is the analysis phase. You start with your conceptual design. You identify potential hazard scenarios and analyze the likelihood and consequence of each scenario. From this, you can identify safety instrumented functions that will safeguard against the hazard and determine the target safety integrity level of your safety instrumented function. In the realization phase, you'll determine the architecture and equipment for your safety instrumented function and validate that it achieves the target SIL. Finally, in the operation phase, you want to perform proof tests, routine maintenance, and record failure rate data for analysis in the future. So that's a good overview of the safety life cycle, and as you can see, it's kind of a closed loop. At any point, if you want to modify your system, you can move back to the analysis phase and redo all the tasks to modify your safety instrumented function or safety instrumented system. So to show you exactly how we would do this, we put together a sample problem. In this example, a batch reactor makes a product from mixing materials A and B in the presence of a catalyst that is contained in material B. The reaction is exothermic once it is initiated, but it requires a sufficient temperature for initiation to begin. During the reaction, there is some gas formation that must be vented. Here I have a process flow diagram of the sample problem. As you can see, there are already some interlocks and process loops in place. There are some alarms indicated here as well. Just from a inlet and outlet feed perspective, we have feed A coming in here. We have feed B coming in here. We have some valves in place on those lines, and then the product would exit the reactor here and go to storage. We also have some temperature control. We have chilled water coming in here and hot water coming in here. They both lead to the jacket around the reactor depending on if you want to raise the temperature or lower the temperature. We have an agitator. a quench tank, just in case the contents of the reactor need to be dumped. So this is your basic batch chemical reactor. This is your starting point before analysis of your safety instrumented system even starts. From here, I can begin with phase 1. We want to start with the process hazard analysis. To do a proper analysis of your process system, you want to be equipped with the right information. That includes your piping and instrumentation diagram and/or process flow diagram. This process should be divided into small pieces so that you can go through the process step by step with thorough analysis. On a description of safety instrument functions. So if you have systems that you can learn from, you want that information on hand. Likewise, you want relevant information from past projects such as likelihood and consequence data. So anything that you can use during your analysis to aid knowledge of the system and do a thorough analysis. So I like to think of the process hazard analysis as a brainstorming session. You want to ask a lot of different questions during this stage. These questions include, what could go wrong? The answer to what could go wrong is a deviation in the PHA. The deviation is a challenge to a process parameter. So, for instance, you could take pressure or temperature and say, what would happen if this parameter gets too high or too low? What would happen if flow stops in the system or is misdirected? From there, you want to ask, how could this go wrong? What is the cause of the challenge in the process parameter? To figure this out, you want to study the P&ID for each node to determine what sequence of events could lead to the deviation. You also want to determine the likelihood of this event. How often could this happen in our process? From there, you want to ask, how bad could it be if this happens? The answer to this question is your consequence. The severity of your consequence can range from lost time injury to number of fatalities. Sometimes, if it's not a safety hazard, but instead a business or environmental hazard, instead of the magnitude of the injury, you might say, how much money could the company lose if this happens? Or what could be the impact on the environment if this happens? Together, severity and likelihood determine your risk. Once you've figured out if this is a high-risk scenario, you want to ask, how can we prevent it? The answer to this question is your safeguards, and you'll want hopefully a number of safeguards in place for a high-risk scenario. Examples of a safeguard include operator intervention, relief devices, or independent protective functions. Your next question should be, how can we learn more? Perhaps you don't know what safeguards are best, or if you need more safeguards. In case you can give a recommendation or a future task assigned to somebody for further review. The other thing I want to mention is that a process hazard analysis needs the right people in the room to give multiple perspectives to the analysis. So you're going to want a process engineer, process control, somebody from the process safety group, an operation and maintenance engineer, as well as a facilitator and a scribe. So in this case, we're going to focus on a high pressure scenario for the batch chemical reactor. So what if the reactor pressure gets too high? What would cause high pressure in this scenario, and what is the likelihood that this cause would occur? If it happens, what are the consequences, and how severe are the consequences? What safeguards can we put in place to make sure that nothing happens? So for this, we're going to go back to the PFD. And I'm going to say, you can see here that there is a vent line to an incinerator. So the only way that pressure should get too high in the reactor is if for some reason that fails or the valve is blocked. So that's why I have this X here. If that should happen, we next have this PT501 right here. So the normal operating pressure in the reactor should be 10 psig. If this vent valve is blocked, then there will be a high pressure alarm at 15 psig. In this case, the operator will have to act. He should do something, or she should do something to mitigate the hazard, to keep pressure down. If that doesn't work, the pressure is going to jump to 20 psig. In this case, the reactor should shut down. Also at 20 psig, PT501 is going to detect the high pressure and set off an interlock that will open this valve to the quench tank. This valve, sorry about that. This valve will dump the reactor contents into the quench tank, and that is XV501. So remember that for the future. If for some reason the pressure is still rising, there is a rupture disc right here that will lift at 60 psig. So as of now, that is our process, and those are the actions that should occur if the pressure gets too high. Keeping that in mind, we can begin our PHA. As you can see here, I've already filled out our facts tool in exida. One thing I want to highlight are the smart deviations on the side. So I already talked about how during the PHA, deviation should be identified. In this case, our node is the reactor. So exida pre-populates a number of deviations that you would want to analyze for a reactor. You'll notice there are green check marks next to each deviation. The reason for that is not because the deviation necessarily applied to this process, but because we want to keep track of everything we've considered. In this case, we're going to focus on high pressure. So I'm going to zoom in. So here you can see I've listed the cause. The cause is that blocked vent valve. Usually, the high pressure would just vent to the incinerator, but in this case, if the valve is blocked, then we might have a hazard. You can see next to that, we have category L. This is our likelihood. We rated it as a 4. What you can't see is that 4 correlates to a frequency. How often would this happen? And we've decided that it would happen a certain amount of time per year. Now we analyze the consequence. In section number 1, you'll see that I have listed overpressure leading to excess temperature and runaway reaction. This could cause a potential vessel rupture. The category is severity. The severity is listed as 5. 5 we associated with an on-site fatality. So if the reactor ruptures, someone could get seriously hurt, if not multiple people. This puts the risk at category 20, which is red. This proves to us that this is something that should be analyzed. It's something that should be taken seriously. We'll need to assign safeguards and then analyze those safeguards in the layer of protection analysis. So next I have the safeguards listed. We know we have a high pressure alarm, a high pressure alarm, and what we're going to call here an independent protective function. That was the PT501 that opens the valve to the quench tank. So it's going to dump the reactor contents. And finally, we have PSE 500, which is the rupture disk that lifts at 60 psig to vent to air. Those are our 4 safeguards. In this case, we assume that these 4 safeguards will reduce the likelihood of a hazard to level 2, which is obviously less frequent. In this case, that would mitigate the risk to a certain extent. But we have a recommendation to evaluate IPF 501 to make sure that it's safe enough, that the equipment involved in that independent protective function, it doesn't fail too often, because we want to depend on that to guard against the hazard. Like I said, we want to analyze this in the layer of protection analysis. So in exida, you can actually link it right here. I select yes, we want to analyze this. I press this button, and it allows me to define the hazard scenario. Here we have runaway reaction from decomposition. If they're later in the PHA is a high temperature deviation that also leads to a similar to runaway reaction from decomposition, I can link that hazard scenario to that consequence cause pair, and that will show up in my LOPA as well. Now, I've talked about the LOPA a couple times, but I have not defined it for you yet. So I'll do that now. LOPA stands for Layer of Protection Analysis. The objective of the LOPA is to evaluate all safeguards as independent protective layers against a hazard scenario. The likelihood of the cause is multiplied by the probability of failure in each IPL. The resulting frequency is compared to the industry's tolerable frequency. If your actual frequency does not equal the tolerable frequency, a target risk reduction factor can be determined for each IPL. So that might sound complicated, but once you see it in the tool, I think it should make perfect sense. I just want to highlight here that in exida, all you have to do is push this button, and your information from your PHA will transfer directly into your LOPA tool. It is that easy to transfer your valuable information over. That valuable information includes your initiating event, which is actually what you listed as a cause in the PHA. So that is our block vent valve. Similarly, it transfers over your safeguards. So here they're listed as IPLs, or independent protection layers. You can see here the high pressure alarm, high pressure alarm, are independent protective function, and your PSC 500, which is the rupture disk. What we're doing here is we're multiplying the frequency of the initiating event by the probability of failure on demand of each of the IPLs. Now, only 2 of the failure rates are known in this case. We know the failure rate of the high pressure alarm here, and the rupture disk, and these are industry averages. We haven't assigned a failure rate to the high pressure alarm because it's only appropriate to consider one of the alarms. If the operator fails in one case, then we can't expect him to respond for the high alarm. And for our independent protective function, we simply don't know what equipment will be selected, so we don't have the failure rate in this case. So as you can see, our intermediate frequency is 1 × 10⁻³ . That does not match our tolerable frequency, which is lower. In this case, we have a risk reduction factor of 1 × 10⁻². This will be important when we move on to the realization phase. But we can also frame it a different way. As you can see here, instead of having a general risk reduction factor, we've calculated what we want the probability of failure to be for our IPF. We're basically assigning that extra risk reduction factor to this IPF, and we're determining that this will be a SIF. In this case, our target frequency matches our actual frequency just as we want, and we can move forward knowing that this is our target risk reduction factor for IPF 501. Just to make this a little clearer, if I were to select more detail on IPF 501, in the LOPA tool, it would look like, oh, just one second. Let me explain a little bit more here on SIL selection. So for each SIF defined, just like IPF 501 in the LOPA, the risk reduction factor is the ratio of the actual frequency of the hazard divided by its target frequency. So the value of this factor correlates to a safety integrity level as shown in the chart below. So you saw earlier that our risk reduction factor was 100, and that correlates to a target SIL of 2. So as I said, if you were to open the detail on the IPF in the LOPA tool, you would see this. This PFD has been calculated, as has this risk reduction factor. In this case, the risk reduction factor is 100, and therefore the target safety integrity level is SIL 2. Now we can take this information and we can write a safety requirement specification. So the safety requirement specification outlines the purpose and target SIL of each SIF. It should answer a few questions. These questions include, what is the safe state of the process and the safety instrumented function? What equipment needs to be protected? What actions have to be taken to protect the equipment? And what is the response time, of those actions? This document should summarize the findings from the entire analysis phase of the safety life cycle and become the guideline for design and realization. So in this case, we just have one safety instrument and function that we are reviewing, but often you have a number of them. The Excellencia tool has an SRS module that allows you to populate all this information. Much of it will come from your PHA and LOPA. Some of it might need to be user defined. However, once it is input, you can export it into a report, which I'm showing here. Excuse me. Right here. And that should be your complete SRS. And that wraps up the analysis phase of the safety life cycle. With your SRS, you can start the realization phase. Realization starts with SIL verification. So for each SIF, the achieved SIL is the lowest value of the following factors. You will have a SIL level based on the probability of failure on demand of each piece of equipment in your safety instrument and function. You will have a SIL level based on the minimum architectural constraints of each element in the SIF and based on the systematic capability for each piece of equipment in the SIF. So as we know, our safety instrumented function has a pressure transmitter, a logic solver, and a valve. We're going to take a deeper dive into each of these factors, but the point here is to specify your equipment such that the SIL level of each of these factors is matching your target SIL. So the PFD calculation is based on many parameters, including failure rate, failure modes for each device, mission time, your mean time to restore, probability of initial failure, redundancy, proof test intervals and proof test effectiveness, as well as your site safety index. This is a pretty complicated topic, so instead of delving any deeper into it, we have a white paper on the exida website called Key Variables Needed for PFD average calculation. That should show you exactly how you might do the calculation. In my case, I simply use silver, and that does the calculation automatically when you model your SIF in the module. For your SIL level based on systematic capability, you want to select equipment that is IEC 61508 certified or have a proven and use justification documented. The objective of this is to ensure that there is no systematic failures for the application that the devices are used in. And finally, you want minimum architectural constraints based on the redundancy levels of your SIF. So during SIL verification, you will put together a conceptual design by modeling the safety instrumented function, and this will determine your redundancy. In some cases, the quality of the failure rate data must be validated per IEC 61508 Route 2H. So if you're not familiar with this term, we do have a webinar specifically on this. Again, it is a deeper topic that does not fit into this overview, but we have a webinar on Exida's website. What architectural constraints does my device meet, and what does that mean? That is dated January 2016. So if you need any more information on that, I would suggest you go to the webinar. So now we can start modeling our SIF. We want to start with the sensor. In this case, that is our PT501. You might see here we have specified a specific model number manufacturer sensor. This is from our Safety Equipment Reliability Handbook, full of failure rate data for devices in the industry. We actually have published this as a textbook, but if you have Excellentia, you don't need that because it's built right in and you can select it with the click of a button. Along with the classification on the side here, that should determine your probability of failure. Also defined here is your proof test interval, your proof test coverage for the sensor, your mean time to repair, etc. So these are the parameters that go into the PFD average calculation. Once your sensor is defined, you can move on to specify your logic solver. This looks a lot the same, but you can see now we're working with the logic solver. We have selected this piece of equipment, and you'll see mean time to repair, proof test interval, proof test coverage, etc. And finally, we specify the final element. You can see here, this is our XV500. We have chosen a solenoid here, as well as an actuator valve combination. We have specified open to trip here, and again, the same parameters you're used to seeing. Once your equipment is specified, you can go to the SIF summary, and here you'll see the entire SIF. You'll see the SIL level based on each of our factors, so probability of failure on demand, architectural constraints, and systematic capability. And at the top you can see the final achieved SIL. Down here a little lower you can see the different average PFDs for each device right here, mean time to fail, and your SIL limits. You can also have little graphs here so that if you're not achieving your SIL level, you can see what is contributing most to the PFD average, and perhaps go back, select a different piece of equipment from the SCRH, and go from there. In this case, we have achieved SIL 2, which is what we selected in the LOPA. That was our target sill. So this has been successful. The silver module does output a cause and effect matrix. So this is pretty simple because it's one CIF, but you can see the PT501 is listed as high trip. You can see our set point of 20 PSIG right here, and it shows that it is going to open the XV500. But that is not all silver does with the resulting information. The next step would be to program your PLC. So information from silver must be converted to application program function blocks. This information includes inputs, outputs, voting arrangement, and trip delays. In Excellentia, the CIF can be imported from silver and converted into delta V for automatic programming of the PLC. So here you can see PT501, XV500, as you would model your CIF in delta V. This is new functionality. This is probably the first time I've talked about it in a webinar. And without diving too deep, I want to say that we are going to have a webinar that talks more about this functionality in early February. So that is the end of phase 2. We're going to move on to operation and maintenance. Here we have to do life event recording. So to demonstrate compliance with the safety standards, you must collect data during the life of your plant and compare it to your conceptual design. During SIL verification, you had specified proof tests, their intervals and effectiveness. During analysis, you assumed failure rates and the frequency of process demands. So this is something you want to record as your plant is running. As of the 2016 revision of IEC 61511, performance of functional safety assessment after gaining experience in operating and maintaining your system is required. So that's stage 4 of the safety life cycle. I believe it was always suggested, but at this point it is a requirement. So you want to make sure you record your proof tests, your field failures, and your process demands. You can do that with one of our tools. We call it SILStat. That is what my screenshot here is showing. This is a proof test recording. In SILStat, we try and make it really easy, so the proof tests are pre-populated. You can simply take your device out into the plant, follow the steps, input the necessary values, see if you passed or failed, and then hit save. This will be saved in a large database of your proof tests, maintenance events, device failures, process demands, etc. So that is proof test recording. You also want to record device failure. So in this case, I'm showing that PT501 failed. Here in SILStat, you can record when it failed, how it failed, what your corrective action is, and the date of your corrective action. You can then add a comment, save, and again, it goes into that same database where you keep track of everything that is going on in your system. I also want to record process demands. So like we said, in the PHA, in the LOPA, you have your cause, your initiating event. We assumed a frequency there, and you want to be able to validate that frequency by recording your process demands. So in this case, we have our hazard scenario. This tool will list your independent protective layers. You want to record which one succeeded in preventing the hazard, which will also indicate that some may have failed. So in this case, if the high pressure alarm succeeded, then great. You have recorded that the process demand happened and that your high pressure alarm i.e. operator intervention, was successful. But if it's your SIF that prevented the hazard, then you have to record also that your operator intervention safeguard failed. So that is it's a lot of information, and you want to record all of that data. Again, that will be saved and stored in a database. My next slide, this shows in SILSAT the event viewer. So this will be all your proof tests, routine maintenance, and any failure information that you need for your system. It's nice, it's all in one place. It can be filtered. You can view it any which way to see exactly what you need. So the reason life event recording is important is because you want to compare your actual performance with your assumed performance. As I said in the analysis and realization phase of the life cycle, a few assumptions are made that hopefully apply to your site. But if they don't, you want to know that as soon as possible. If you collect enough data and you find that your risk reduction is adequate, then great. This is the perfect scenario. You can continue to collect data and maybe use it when you are analyzing a system in the future, a similar system. If your risk reduction is inadequate, however, your hazard risk is higher than expected, you want to return to the analysis phase for redesign and implementation. This means your site is not as safe as it should be. You're going to need to go back and fix that. Now, if your risk reduction is more than adequate, if you've collected a ton of data and you find that your system is over-designed, this allows you to modify design practices for the future. So in your next analysis for a similar system, perhaps you can save some money by not over-designing your safety instrument and system. But in all cases, as I said, data collected and lessons learned during operation of a plant can be used for analysis of new process systems. So it never goes to waste. And that is where I will end the Phase 3 operation and maintenance phase of the safety life cycle. I do have this slide here. It's a nice overview. Again, you saw this earlier, but here I want to highlight that everything you saw today was excelentia or SILSTAT. We do have tools and modules for each main task in the safety life cycle. So I had showed you today the PHA, LOPA tool, select, process SRS, you saw silver, and you saw SILSTAT. Like I said, this is a closed loop, so you can always go back to the beginning. If you use excelentia and you saw something here that you didn't know we could do, then you can ask us to see how we did it. If you don't use excelentia and you do it a different way, perhaps you can share that with us, or maybe you're interested in using this software tool. If you want to know more, we are having a SIL selection and SIL verification training course. You can learn how to do these tasks with excelentia. We're having the course February 14th and 15th. That is Valentine's Day, but I will be there, and so you should come over to Houston and join us for that. There is a link. I can send a link along with these slides at the end of the webinar, or you can go to exida.com and you can find all of our training there. This isn't the only training we have available, but it applied to what I talked about today. So you can go on the website and take a look at all of the training we're offering. In addition, you can join us at Texas A&M. We are exhibiting and presenting at the Instrumentation and Automation Symposium on January 24th through 26th. I will be in the booth doing software demonstrations along with E1, and we have someone presenting as well. So if you're going to be there, come say hi. If you were on the fence, you should come and join us. And that is it for the webinar today. I hope that you learned something, or that I have helped you brush up on some of the different phases of the life cycle. I do have some questions here, but I'm going to answer them in an email. So what we do is we get all of the questions in an Excel spreadsheet. I can collect them and make sure you get thorough answers. In addition, the webinar will be sent out. You'll get the slides in an email afterwards. So hopefully, if you have any questions or if you want to review, you'll get that. So that's it for today. Thank you so much for listening in. And I think we mentioned this in the last webinar, but if there are any topics you want to hear in the future, please let us know, and we'll try and do a webinar on that as well. Okay? Thank you. Have a good night.